In this video, I'm going to talk about the mole. All right, so the mole is a chemist's amount of things, period. So farmers have acres, bakers have dozens, and chemists have moles. Okay, so a mole is Avogadro's number. Okay, it's 6.022 times 10 to the 23rd, and that is something you should have to memorize. You should memorize. You need to memorize for class. So 6.022 times 10 to the 23rd. And where this number came from is that it was arbitrarily chosen how many atoms of carbon-12, of the isotope carbon-12, are in 12 grams. Because remember, we learned that the isotopes weigh, right? If it's carbon-12, it weighs 12 AMU. So Avogadro found out how many exact number of carbon atoms were in 12 grams of carbon-12. And it's this number, 6.022 times 10 to the 23rd. Okay. The units on that, so you would say that that's how many atoms or molecules or ions, so it's the amount per 1 mole. Okay, so that does have units. So sometimes I just say it's the number per mole. Okay, and for every element on the periodic table, if you look at the formula masses, you can see how many grams, the average number of grams it takes to have 1 mole's worth, so 6.022 times 10 to the 23 molecules of that element on the periodic table, which is just giving you a couple different masses here. Also, just to kind of show you that it's not all the same, so 1 mole of a compound like octanol, which is an alcohol, is not the same. So look how much volume that takes up, 1 mole. So that's 6.022 times 10 to the 23 atoms, or I should say not atoms, molecules of octanol here. But this is methanol, which is a lot smaller in its structure. And look, it only takes up about the third of the volume. Okay. Here's sulfur. Remember that elemental sulfur is S8, and you would need about 300 grams, so it's 256.5 grams of sulfur to give you 6.022 times 10 to the 23 molecules of S8. Okay, and then this is mercury 2 iodide, and so you only need, well, not you only, but you need about 500 grams of mercury 2 iodide so that you have 6.022 times 10 to the 23 molecules of mercury iodide. All right, so let's look at some problems. So we use Avogadro's number in a few different ways. So one thing that you'll see is, so we're going to use a lot of the times, we're going to be using molecular mass and Avogadro's number. Okay, so if the question wants you to convert mass to moles, you'll have to use the molar mass. So the molar mass of the compound is in units of grams per mole. So it's a link of how you can link between grams of this compound to moles of the compound. Okay, so for example, according to the nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in moles? So see, the question is providing you with grams and wants you to calculate how many moles that is. So to figure out how many moles that is, we'll have to use the molar mass of potassium. So you'd have to look on your periodic table for the molecular weight of potassium, which is 39.10 gram per mole. Then you set up your dimensional analysis table. So you have your starting value, 4.7 grams, and then potassium, and then you multiply it by, or divide it by, the molecular weight. So it's 39.1 gram for every 1 mole of potassium. So notice that grams cancel and you're left with moles. So 4.7 divided by 39.10 equals 0.12 moles of potassium. Okay. So you'll be doing lots of dimensional analysis tables here. What if we're given moles and want to go to mass? So again, the link between mass and moles is going to be our molar mass, right? Grams per mole. So the link to mass and moles, you always use molar mass. If you start with moles though and have to get to the mass, instead of dividing by the molecular weight, you'll multiply. And you don't have to remember, oh, do I divide or do I multiply? You let your dimensional analysis table set it up for you so that your units cancel, and then you just perform the mathematical operations, right? Multiply all the numerator values and divide by all the denominator values. So let's see, a liter of air contains 9.2 times 10 to the 4 moles of argon. What is the mass of argon in a liter of air? So we start with our moles are given, and then we know that the link between moles and mass, or moles and grams, is molecular weight, right? Because it has the units of gram per mole. Got to go back to your periodic table and find argon on here. It's a noble gas, 39.95 grams per mole, okay? So if I know how many moles I start with, then I need to cancel out my moles. And here's the molecular mass. Remember, it's 39.95 grams for every 1 mole of argon, right? So moles cancel and it's left me with grams. So when I take this value and multiply it by the molar mass of argon, I get 0.037 grams of argon. Okay, so see, we've been using molar mass a lot. And those were just looking at some elements on the periodic table to convert between mass and moles. But what if you have a compound? So now we're getting bigger. So many atoms in a single compound, right? So vitamin C is a very large compound, well, larger than the ones we've been talking about, which are just elements. But so C6H8O6. So it's recommended that children between 4 and 8 years, consume 1.42 times 10 to the negative 4th moles of vitamin C. So the question's asking is, what's the mass of this in grams? And thankfully, instead of sitting here and calculating the formula weight by yourself, they give you the formula weight of vitamin C already. Okay, so here again, so we're given moles, we need to calculate mass, and we have to use molecular weight because the unit, again, is gram per mole. So that's going to link those two. So I start with what I know, and you know what you're given, which is 1.42 moles of vitamin C. And then it is 176 grams for every 1 mole, right? So make sure you line up your dimensional analysis so moles cancel, and you'll be left with grams. So that is 0.025 grams of vitamin C. Lastly, what if we want to start with grams and get all the way to the number of atoms? Okay, so now we're going past moles, and this is where we have to use Avogadro's number. So Avogadro's number, remember, has units of number of things per 1 mole. All right, so the question is, a packet of artificial sweetener contains 40 milligrams of saccharin. Here's the molecular formula of saccharin, and here's the structure of saccharin. Okay. Given that saccharin has a molar mass of 183.18 grams per mole, how many saccharin molecules are in 40 milligrams of saccharin? So thankfully, I'm thinking in my head, so we got to go grams to moles, then moles to number. Okay, that's going to be the progression. So to go grams to moles, remember, molar mass, because it has units of gram per mole. And then to go from moles to number of something, you have to use Avogadro's number because the units of that are the number per mole. Okay. So here's that kind of laid out. So first we convert mass into moles, and we're going to have to use the molar mass. And again, if you don't remember, oh, do I divide or multiply, we're going to let the dimensional analysis cancel out for us. Okay. Then we have to go moles to the number of molecules, and that's going to be Avogadro's number. So we start with the grams. So we were given milligrams, but you have to move the decimal place 3 spots to the left to get that to grams. So 40 milligrams is 0.04 grams of saccharin. Okay, so I'm starting with grams. Now I got to get to moles. So here's my molar mass. It's in grams per mole. So I would end up dividing my start by the mass, okay, because look, grams cancel. So now I'm in moles of saccharin, and now I have to finish by getting to numbers. So if I'm in moles, I have to use Avogadro's number, because this is the 6.022 times 10 to the 23 number of molecules or atoms or whatever it is, right? This word can change depending upon what you're looking at, but number for every 1 mole of it. So then I cancel out moles and I'm left with numbers, okay? So that gives us this many total molecules in 40 milligrams of saccharin. So now here is the thing that you can take it one step further. So if it answers the question of how many molecules are in 40 milligrams, but what if it said how many carbon atoms are in 40 milligrams? So we were starting with our 40 milligrams and we got all the way to the number of molecules, but we want to know specifically how many carbon atoms are in 40 milligrams. And notice that the formula tells us that for every one molecule, you'll have 7 atoms of carbon, 5 atoms of hydrogen, 1 atom of nitrogen, 3 atoms of oxygen, and 1 atom of sulfur. So we're going to have to use this 7. Okay, so we take the number of molecules that we just solved for and multiply it by this new stoichiometric ratio, which is 7 carbon atoms in every 1 molecule of saccharin. And so if the question was asking how many carbon atoms, that's how you solve for that value there. So it'll be 7 times the amount of the number of molecules that you have.